Finally, let's talk about a chosen ciphertext attack on RSA. This is the first time that we've considered this sort of attack in this class. And one reason we're doing it now is because it actually works here. So it turns out, it's a little bit scary, that this kind of attack might actually be successful against RSA if Alice's machine is actually set to respond to any decryption request. And we'll talk about this a little bit later. So the only upside to this is that this kind of attack will only reveal a single plain text message to Eve. It will not give Eve Alice's private key D. It'll only give away a message. Still, though, that could be dangerous, especially if that one message was your credit card number, right? So let's talk about how Eve can execute a chosen ciphertext attack on RSA. Okay? So Eve has the ciphertext message C, and she wants to steal the plain text, right? So she knows what the ciphertext is. Everybody does. And she wants to steal the corresponding plain text. All right, that would be your credit card number. All right. Now she knows, of course, that C is M to the E mod N. She knows that, but she can't take E throughs. So that does not help her find out what M is, right? So she's sort of stuck there. Eve also knows that the plain text is C to the D mod N, but that's even worse because she doesn't know the decryption key D, and nor does she know M. So she's got two unknown variables here. So this is even worse. So it seems like she's stuck, right? It seems like there's no way for her to actually get the message. But there actually is. Let's talk about how Eve can recover this message. It requires Alice to make a mistake, though. That's the one takeaway from this. All right. So if Alice or her machine, which is more realistic, is enough of a sucker, Eve can execute the following chosen ciphertext attack and actually get the plain text M. Okay. So as you read this, be a little impressed how this works. Eve is going to be able to get M, but she's going to be able to do it without ever knowing the decryption key D. She doesn't need to know it. She can still get it because Alice is going to make a mistake. And this should bother you a bit. So let's talk about how Eve gets this message. So here's what she does. First, Eve selects an element R mod N. All right, this is called a mask, okay, a masking element. And she chooses her masking element R mod N so that it has two properties. Okay, the first property is it ought to be invertible mod N. Okay, so she needs to choose an invertible element mod N. Okay. That's not hard to do. There are lots of things that are invertible. You pick one at random and make sure it's invertible. Then what she does is she computes C times R to the E. Now R she knows because she picked it herself. E is public, so she can do that too. And C she knows because it's ciphertext, and everyone is allowed to know ciphertext. And so what she does is she computes CR to the E, and she makes sure that the resulting message here does not look fishy to Alice. All right, I'm using F. I'm calling this F because it's going to be a fake message. Okay, so Eve makes sure that the fake message F, which is CR to the E, doesn't look suspicious. All right. Then what she does is she executes a chosen ciphertext attack on Alice using this message F. All right, what that means is that Eve asks Alice to decrypt F for her. All right, so Eve will request the decryption of F, and Alice will unfortunately make the mistake of responding. Okay, now why would Alice ever respond? Well, she might do it because the message F doesn't look suspicious. All right, it doesn't look like it has anything to do with secrets like M or C. She might also do this because Alice is a computer. She's not a person, so she might not know any better. She might respond to any request that's made of it. She's a machine, okay? So if this happens, then Alice will decrypt F. And how does she decrypt F? She goes F to the D, right? So Alice might decrypt F and compute F to the D and call the verdict U, and she'll tell Eve the result U, right? Now, of course, Eve does not need to know D. She doesn't know D. So she doesn't have any idea how Alice computed U, and unfortunately she doesn't have to know. What Eve does is she will compute U times R inverse, and that will be the plain text message, unfortunately. Right? So let's see and do this with a concrete example to watch this work. Okay? It's kind of amazing to me this works. Suppose that Alice's bank reset her PIN for her ATM to be the plain text PIN 3105. And they need to tell her this, but they won't send it to her unencrypted, of course. They're going to first encrypt it under Alice's public RSA key and then mail it to her, all right, in the encrypted PIN, okay? So they look up Alice's public key data and see the information here, and so the bank computes the ciphertext, which is the plain text PIN 3105 to the encryption exponent 141, mod 10057, and they get 9963. So they send the ciphertext 9963 to Alice. right? Alice can then decrypt that in private with her private decryption key, and she'll learn that her new pin is 3105. So far, so good. Everything's above board. Nothing illegal has happened. Okay. However, Eve breaks into Alice's mailbox and she sees the ciphertext message 9963. Right? Eve selects her mask R to be 1715, which remember it has to be invertible, and it's got to be invertible mod 10,057. So Eve checks that and learns that, yep, she's fine. The inverse is 6345. Right? So now Eve forms the fake message C R to the E. There's the ciphertext the bank sent to Alice 9963. There is the mask that Eve chose, 1715, and there's Eve's encryption exponent, 141. And she does all this math and gets 7847, which looks like it has nothing to do with 3105, right? There's no relation between 7847 and 3105. So Eve is now going to trick Alice into decrypting. She says, hey, Alice, would you please decrypt 7847 for me, right? So Alice makes a mistake of actually decrypting this fake message 7847. She says, yep, I got 4922 for the decrypt. And Eve says, thanks. And so now Eve will set U to be 4922. And so what's supposed to happen here, if I'm telling the truth, is that Eve computes U times R inverse, and that will be Alice's pin of 3105. Is it? Well, unfortunately, yes, it is. When you do U times R inverse, you get 4922 times 6345, and that turns out to be 3105. So that does give away Alice's unencrypted pin. That's not good. So this is pretty amazing. By making one little slip up, Alice has allowed Eve to uncover her plaintext without even knowing the decryption key. Right? So let's close by seeing how this works. Okay? Why does this work? Well, it's not too bad, actually. I need to prove for you that with the mask R, the fake message, and the decrypt of the fake message, Eve will always know that the plaintext M was UR inverse. And here it is. The key observation is that this whole thing is happening inside of a valid RSA system. And since it's a valid RSA system, any message to the ED has to be the original message, because this is R that was first encrypted and then decrypted, and that's going to be R again. So the mask that Eve chose is going to end up being R when it goes through a round of encryption and decryption. And so what is UR inverse? Well, here is UR inverse. Let's just substitute. U was F to the D. It was a decryption of F. So U is F to the D. What was F? F is CR to the E. So this F is CR to the E, all to the D, times R inverse. But use your laws of exponents right here. This is going to be C to the D, R to the E times D. C to the D, R to the E times D, R inverse. But R to the ED is R. So this R to the ED is an R. So the R and the R inverse cancel, and you get C to the D. But of course, ciphertext being decrypted is unfortunately the plaintext. So that is why UR inverse is equal to the plaintext. So you've learned something here. This is a big lesson. In order to defend your RSA system against a chosen ciphertext attack, never, ever, ever respond to any request to carry out any decryptions with your secret key, and it doesn't matter who asks. If you ever do that, that person could secretly be running this sort of attack on you, and you wouldn't know it. So be careful out there. You could be vulnerable to a chosen ciphertext attack, but you're safe as long as you never respond to any request to ever decrypt any messages.